everyone. So the goal of today's talk is to discuss some results about chi-boundedness properties of geometric graphs, or more precisely of almost chi-boundedness properties of geometric graphs. So my goal is to kind of give a general approach to how to attack many of such problems. But for this, let me start by talking that what is chi-boundedness. So I'm sure many of you in this group are very familiar with this notion, but still let me give a brief overview. So as we all know, in every graph, we have that the chromatic number of the graph is at least as large as the clique number of the graph. And despite the naive feeling you might have that there is some stronger connection between these two parameters, it's well known that the chromatic number of G cannot be bounded by any function of the clique number. So more precisely, it is already known in the 50s that there exist graphs which are triangle-free but have arbitrarily large chromatic number. For example, one such graph is the Michelski graph. But actually, thanks to the emergence of the probabilistic method, we now actually know much more. We know that the chromatic number of a triangle-free graph on n vertices can be actually quite large. So thanks to probabilistic methods, now we know that there exists G graph. G is n vertices, triangle-free, and the chromatic number of G is almost as large as square root. So this is due to a result of Spencer, which was done. So this error term was improved by Kim, and now we know the worst kind of dependence of the chromatic number of triangle-free graphs up to constant factors. However, as I mentioned, this construction is kind of probabilistic, and people observe that if we restrict our attention to some more structured families of graphs, then these bounds can be greatly improved. And in some cases, we actually have that there is some dependence between the chromatic number and the clique number. And this is especially true in geometric families. So one of the maybe the most well-known examples is due to Asplund and Ramsey. So this is from the 60s. They proved that if G is the intersection graph rectangles, and actually the chromatic number is at most some constant times the square of the clique number, so it's whole clique number. So here, every time I talk about rectangles as boxes, I always mean that they are axis parallel. So this theorem shows that if we restrict our attention to this very structured family of graphs, which are the intersection graph of rectangles, there is actually some dependence between these two parameters. And let me mention that now, due to a very recent breakthrough of Sharamsuk and Bartosz, we now know that actually this upper bound can be improved to just omega times log omega. Okay. So now this motivates kind of the question that what are those families? So what can we say about those families where there is actually some dependence on the dependence between the clique number and the chromatic number? And for this, we define the so-called chi-boundedness. So we say that a family of graphs is chi-bounded if there exists some function from naturals to the naturals, the positive integers, such that for every member of this family, the chromatic number of G is bounded by this function of the clique number. So by this definition, intersection graph of rectangles are chi-bounded. And now this question whether which families are chi-bounded was systematically initiated by Gyárfás in the, so I believe it was in the 80s, maybe end of the 80s. So where he proposed to study both the chi-boundedness of geometric families and also the chi-boundedness of families which avoid some small induced subgraphs. But now in this talk, I want to concentrate on geometric families. Okay, but now let's go back a little bit to this result of Aspen and Grunbaum. So next natural question after seeing this theorem would be to go to higher dimension. Is it true that intersection graph of boxes in, let's say, R3 are chi-bounded? Now this, however, turns out to be false. So it is again a famous result of Berling, or more like a first construction of Berling. In the 60s that there exists triangle-free intersection graphs of boxes in R3 such that the chromatic number grows as some constant times log n. So unfortunately, the moment we go into higher dimension, this chi-boundedness is no longer true. However, we can still say something on the positive side. So there is a folklore result, or I'm not really sure who to attribute it to, but it can be proved using a simple divide and conquer argument that the chromatic number of such graphs, so the chromatic number of intersection graph of boxes can be always bounded by a polylogarithmic function of the number of vertices. So more precisely, G is the intersection graph of boxes in RD. Then the clique number of G, the chromatic number of G is at most some constant times where the constant depends on the clique number times log n the d minus 2. And here this constant is actually the constant you would get if you solve the two-dimensional case. So this shows that while intersection graph of boxes are not chi-bounded, they are still highly structured compared to graphs like this. So where here we have polynomial chromatic number, here we only have logarithmic chromatic number. So this can suggest that it's probably also makes sense to talk about graph families where we have an almost chi-boundedness property. So let me define this. So again, say that the family G is almost chi-bounded if for every member of the family, the chromatic number is at most found to be little o1, where this little o1 depends on the click number. Okay, so by this chi-boundedness, this is an official definition which you can really find in papers. So this is something I am introducing now. I don't know if there is any better expression for this. But and also you could define it in different ways. So you could also ask that maybe you restrict that you want the chromatic number to be at most some polylogarithmic factor of the click number, but this is kind of the least restrictive definition, which still makes sense, which still differentiates between just general graphs and highly structured graph families. Okay. Well, let me use different words. Okay, so in this past 60 years, this question whether certain geometric families are chi-bounded or almost chi-bounded is extensively studied. So let me just give you a brief survey of what's the state of the art now. So let me write here. Let's put on the right the chi-bounded families. Here, let me almost chi-bounded. So as we've seen, we have intersection graphs of rectangles here. And here we can write intersection graph of boxes. Another famous example, which has seen a lot of progress recently, is the circle graphs. So the circle graph is just the intersection graph of course of a cycle. And it was shown by Yarfash that they are chi-bounded, but his chi-bounding function is exponential. And it was very recently, there was a breakthrough by Davison, McCarthy, and Davis, where now Davis determined the chromatic number, the dependence between the chromatic number and click number up to a constant factor. Now, however, another natural family of graphs is the intersection graph of segments. Now, this turns out to be not chi-bounded, but almost chi-bounded. So the fact that it's not chi-bounded is due to Kraftsik and many authors. Sorry, I'm not going to list all of them now, but this is also it was a kind of surprising recent result, because for a long time they believed that this is also chi-bounded. It turns out to be not the case, and also the fact that it's almost chi-bounded follows from a result of Sook, and now it follows from a bunch of other more general results as well. So it's a family that's even more general than this. The intersection graph of curves, which are also known as string graphs. So a curve is just some continuous line in the plane, and then because of, we know that already for segments they are not chi-bounded. Also for this more general family, it's not chi-bounded, but there is a result of Fox and Pock, which shows that they are almost chi-bounded. So they have some the chromatic number is bounded by actually some polylogarithmic function of the clique number and n. So in some sense, this is a very general result, because if anytime we have a kind of any reasonable geometric object in the plane, like some convex set, we can approximate it to the curve. So string graphs represent every intersection graphs in the plane, basically. So this kind of settles the question for intersection graphs. However, there are some other very interesting results. So for example, if we slightly restrict our curves and we require that they are grounded, they then become chi-bounded. So here I can put the intersection graph of grounded curves. So this is due to a recent result of Roque and Bartosz. And so what are grounded curves? So we have a ground, which for me is going to be a vertical line, and then all our curves are on the right-hand side and start from the ground. And if we have the intersection graph of such curves, then they somehow surprisingly become chi-bounded. But so far, I've only talked about intersection graphs, but actually in this talk, I want to consider all kinds of geometric graphs and whatever geometric graph means. But for example, another type of geometric graph is the disjointness graphs, disjointness graphs, so the complements of intersection graphs. And in this case, we also know a lot. So for example, there is a result of Carey that says that if we consider disjointness graph of boxes, then they become chi-bounded. And also another very general result is that the disjointness graph of convex sets are chi-bounded, and this is due to almost 20-year-old result of Larman, Matushak, Pak, and Terechik. And here this can be generalized even a bit further. So instead of convex sets, we can also put X monotone curves. So it's not visible, sorry. So this is here, not here. Sorry for this bad notation. So here a curve is X monotone if it's the graph of some function on some continuous function on some closed interval. And to just give you one more geometric family, which is neither an intersection graph nor a disjointness graph, we also have the so-called shift graphs. So shift graphs were introduced by Erdős and Hajnal in the 60s, and they provide a very good example of triangle-free graphs with arbitrarily large chromatic number. So let me give you a quick definition. So what's a shift graph? So we have the vertices are all the shift graph of order k. So it has the vertices. So the vertices of this graph are the L tuples of integers, satisfying that they are strictly monotone increasing between one and then the edges are those pairs where the last k-1 tuple is the same as the first k-1 tuple of another edge. So this is connected to all, so all edges have this form. And what Erdős and Final proved is that the shift graph order k has chromatic number log 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 k log 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 n, where the log is iterated k-1 times. Yes. Okay, so now we have seen a bunch of examples of geometric graphs where they are either chi-bounded or almost chi-bounded. So now here you can argue whether you want to call this graph geometric or not, but so later I will give you some definition according to which this should be considered as geometric. So after seeing all these examples, you might have this feeling, or you might even formulate a meta conjecture that maybe it's true that every kind of reasonable family of geometric graphs need to be either chi-bounded or almost chi-bounded. But this doesn't seem to be true in this generality. Of course, again, now what do you mean by geometric graph? This is arguable, but to show you a nice family which doesn't belong to any of the two parts, let me give you the Disjoiners graph. Of course. So recently with Andrew Suk, we managed to show that there exists triangle free disjointness graphs. And first, that the chromatic number is at least some constant times and the 1/4. So it really grows the polynomial. And this is actually not even that far from the theoretical best upper bound, which is square root n. So this shows that when we formulate this kind of meta conjecture, we need to be a bit careful. And so actually, if you look at this family, this is quite unique. So this is quite rare that it happens. So this suggests that you should be able to come up with maybe with some general theory or some general condition on these geometric graphs, which really forces that you are either in this category and this category. Like if you're only considering intersection graphs, then this basically solves the whole thing. But again, I'm saying I want to understand general graphs. Okay. So let me erase some. Okay. So, okay, so we try to attack somehow general geometry graphs. But then here's a question, which is that how does general geometry graphs look like, and what kind of description can we give? And so there were already several attempts to do this, and this led to, for example, one very interesting family of graphs, which are called semi-algebraic graphs. So let me talk about this. So this was introduced in the 2000s. And so let me give you a definition. The definition is a bit technical, but I will walk you through it. So I will explain how do these families look like. So now we are considering graphs where we imagine their vertices being points in some finite dimensional space. We're going to say that G is a semi-algebraic graph. Complexity the capital B M if the vertices of G are some points in a d-dimensional space, and also there exist M functions, M polynomials from R to the D to R. These are polynomials of degree f of z, capital D. And the edges of G can be recovered by only considering the sign pattern of these polynomials. So it says whether x, y depends only on the sign pattern of f1 xy fm xy. So what is this? So we have these two vertices. So these polynomials are. So if you have two vertices, they are just 2 points in Rd. We just plug them in this function. In these polynomials, we look at their sign pattern. So we just record whether what we see is a positive number, a negative number of 0. And if just from this sign pattern, I can decide whether x and y was joined by an edge, then I say that these polynomials realize this graph G. And so it turns out that these families capture a lot of geometrically defined graph families. So among these examples that I showed you before, they don't capture everything, but for example, if you look at intersection graph of boxes, then they can be shown that they are semi-algebraic with bounded complexity. So and I forget to say that, so that we are interested in those graphs and those families of graphs where we where these parameters, D, capital D, and M are all fixed. And then for these families, we say that they have bounded complexity as a semi-algebraic graph. So intersection and disjointness graph of boxes are like these circle graphs, shift graphs. They can be all described as a semi-algebraic graph of bounded complexity. So in general, if you have any kind of family of geometric objects and which involve algebraically definable objects, meaning that they can be defined using bounded degree polynomials, then their disjointness intersection graph and all these graphs are typically semi-algebraic. But unfortunately, this doesn't capture some natural families like intersection graph of convex sets or curves and so on. But this still provides us some very general, very general approach to understand geometric families. And so one question that you might ask is that, is it true that such graphs are almost chi-bounded? But even before that, so let me say some known properties of these graphs. So in this Ramsey and covering, or no, more like in the Ramsey setting, these graphs were studied by Alon, Pincassi, Radich, and Sharrier first, who showed that if we have a semi-algebraic graph of bounded complexity, such a graph always contains a polynomial size clique or a polynomial size independent set. So G is semi-algebraic. Bounded complexity. Then vertices then we have that either the clique number or the independence number of G is at least and to some constant where this constant only depends on the complexity. So in particular, these families satisfy the Erdős-Hajnal property if you know about the Erdős-Hajnal conjecture. So then it's natural to ask that do these families have this almost chi-boundedness property? Because if they do, then this would imply a lot of other results, but maybe with some weaker bounds. So unfortunately, this turns out to be false. And quite interestingly, this construction I mentioned you before about the disjointness graph of curves. So our construction with Andrew is also semi-algebraic of very low complexity. So in general, this family is too general in the sense of capturing almost chi-boundedness. But then one can ask that maybe can we slightly restrict this family, or maybe not even slightly, or can we find some interesting subfamily of this which actually does have this property? And one such family is the family of which I'm going to talk about today, is the family of semilinear graphs. So semilinear graphs are almost defined the same way as semi-algebraic, with the additional condition that I want all my polynomials to be linear functions. So in particular, that D will be just one. So, but still, let me just give you a precise definition. So we're going to say that G is semi-linear. Complexity E if the vertices of G are some points in some finite dimensional subspace. And now here, already the first difference is that I don't need to put any restriction on D as a function of T. D can be anything. It doesn't make a difference. Just some points in some finite dimensional space. And again, there exist T linear functions. There exist f on ft, which go from RD times RD to R. So these are linear functions. So these are linear, and again, whether two vertices are joined by an edge, it only depends on the sign pattern of the evaluation of these T linear functions. So again, so this part is just the same. So let me clarify, just to be sure about what do I mean by linear function. So f is linear if I can write, if there exists some coefficient such that fx to xd is equal to some ai xi plus b. So it's very important that I'm not talking about multilinear functions, because the moment I allow multilinear functions, I allow terms of the form xi times xj times xk, then I already don't create a family which is different from this. So then I would just get a family which, so if I would allow multilinear functions, then every semi-algebraic graph of bounded complexity would be also bounded complexity in this sense. So to really have a different family, we need to define linear in this way. And so let me say a few words where these semi-linear graphs come from. So actually they were introduced very recently in a paper of Bazic, Chernikov, Starchenko, Tao, and Trump, where they considered the so-called Turan type problem for semi-linear graphs. So let me create some space. So it's still hopefully visible at the bottom. So sorry, so hopefully this was enough time to look at it. So again, so semi-linear graphs were recently introduced in the context of Turan question, where it was proved that G is semi-linear. Complexity equals T, and also G does not contain a copy of the complete bipartite graph KKK. Then we have the following covariance Student type result, which says that then the number of edges of G is at most some constant times n times log to some constant, where this constant only depends on the complexity of T. So just to recall, I'm pretty sure you're all familiar with covariance Student, but generally, if a graph does not contain KKK, then it can have as many edges as, or we don't know this, but okay, so we can have constructions which show that it can have almost a quadratic number of edges. And also if you consider semi-algebraic graphs, there is a nice construction of semi-algebraic graphs which shows that, again, in this case, you cannot hope for an almost linear upper bound like this. So if you consider the point line incidence graph on the plane, then you know that you can take G to have n points and n lines. But we know that the semi-Reddy-Trotter theorem is sharp, which tells us that such a graph can have constant times n to the 4/3 edges, and such graphs obviously avoid K22. So in this case, you can have much more edges than linear. However, surprisingly, if we restrict our attention to semi-linear graphs, then we immediately get something really non-trivial. So in this case we can go down to almost linear.
So here bounded complexity means that there is a bounded number of those linear functions.
Yes.
Okay.
Yes. So here that's the only parameter. And yeah, in a moment I will show you why you don't need to bound dimension. It's almost immediate. So that here you cannot quite go down to linear, so there exists some simple semi-linear graphs where you need at least one logarithmic factor. Okay. Yes. So let me now show you some examples of semi-linear graphs, because at first glance these families might look a bit too easy, too trivial. So then you might wonder that are there at all any interesting families of semi-linear graphs that can be considered? And it turns out that already among those examples I mentioned, quite a few of them are semi-linear. So just to practice kind of this definition of semi-linearity. So let me show that the intersection graph boxes is semi-linear. Of complexity to the, so if we are in RD. So why is this true? So you can define a box by 2D parameters. You take the minimums of the vertices and the maximums of then the maximum coordinates of the box. So every box can be written as the Cartesian product of closed intervals x1 times y1 times xd yd, where xi is less than yi. And now if you have two such boxes, b and b prime, so b prime is defined by x1 prime, y1 prime, xd prime, yd prime, then you can decide whether they are intersecting by looking at the following polynomials. So you just need to compare. So you define, let's say, the function fi x1. It's the, sorry. So here you just compare the coordinates yi and xi prime, and also you will need to compare yi prime and xi. And if I did not make a mistake, so sorry, I'm doing this a bit from memory, but I think this is right. So now you have that these two boxes b and b prime intersecting if and only if all these 2D polynomials or these 2D linear functions are non-negative, or well, they are, yeah, you need that they are non-negative. So this is one example. And then after seeing a few examples, you can easily find kind of a feeling when is a geometric family of graphs semilinear. So another example is the intersection graph of course of cycles, circle graphs. Because they are also equivalent to so-called interval overlap graphs. So there your family is just, you have a bunch of intervals and then you connect to if they overlap, meaning that they are not disjoint and none of them contains the other. And again, this is a condition that you can just decide by comparing the endpoints of the intervals. So these are just linear functions. And the third example is the example of shift graphs. So if you remember, you had these k-tuples of vertices, and now you just need to check whether the last k-1 elements coincide with the first k-1 elements of another vector, which again you just consider, you just compare coordinates and you look at whether they are 0 or not. Yes, and so now one natural question would be that, especially after seeing this result, is it true that semilinear graphs of bounded complexity are chi-bounded or almost chi-bounded? So of course they cannot be chi-bounded because we already know that for boxes they are not chi-bounded, but at least it turns out that these families are really almost chi-bounded. So let me write up this result. Now the main theorem is that if we have a graph G which is semilinear, complexity T, then the chromatic number of G is bounded by constant times the click number of G to some power times log n to some other power, where all these powers, the C and C prime, they both only depend on the complexity T. So I hope this term is clear. And so just give you a proof. So let me give you a very brief outline of the proof. So actually, in this proof, I don't really need any groundbreaking ideas. It follows from a combination of many known techniques, and it's mostly just about understanding how these graphs look like. So first of all, so I want to skip a few technical details, and let me introduce you a new family of graphs, which can be kind of thought of as building blocks of semilinear graphs. So let me introduce the definition. So let G be quasi comparability graph of complexity T. So G is a quasi-comparability graph of complexity T if the vertex set of G is contained in RT times RT. So these are, so I think of as a pair of points in a T-dimensional space. And we connect, and if we have two such pairs, xy, and RT times RT, and we also have another pair x prime y prime, then we connect them by an edge. So yeah, so joined by an edge. If we have either x is less than y prime, I will define what this less means, or x prime is less than y. So by this less, I mean the coordinate-wise comparison. So this is equivalent to saying that xi is less than yi prime for every coordinate. So this is just the usual partial ordering on the T-dimensional space. So actually, I think this graph family on its own is quite interesting, and I actually don't know if this has been defined before, if something similar has been studied, maybe with some other name. But yeah, so why do I call these quasi-comparability graphs? So if I would have that x equal y for every point, in this special situation, this would be really just the partial ordering, and this would be the partial order of Dirichlet-Miller dimension exactly T, or at most T. So this somehow, so this family, this contains partial orders of dimension T. And so how is this family related to semilinear graphs? So it turns out that every semilinear graph is just the finite union of quasi-comparability graphs. So claim is that if G is a semilinear, complexity, bounded complexity, and there exists G1, GK quasi comparability graphs complexity at most T prime such that G is union all these graphs, where here I mean that they are graphs on the same vertex set, and I take the union of the edge sets. And here the point is that these parameters K and T prime, they only depend on the parameter T. Again, so proving this is not very hard, it's just technical. So just to give you an idea why this is true, or how the quasi-comparability graphs come into the picture. So now if we look at some polynomial, some linear function x1, xt, x1 prime, t prime, then because this is linear, we can write this as some function ai xi plus some bi ai prime xi prime plus b. So anytime when we are looking, we want to check whether this is positive or negative, what we could actually just do is we can group the coefficients, of course, this as in the picture. So this is already grouped. So we can group the coefficients corresponding to the first half, group the coefficients corresponding to the second half, and then let's say we can rewrite this. And so whether this function is negative or not is equivalent to deciding whether we have that sum ai xi plus b is less than or equal to minus sum minus ai prime xi prime. So here, actually, the only thing is important is what this evaluates to, or even taking this, what this evaluates to. So instead of looking at kind of the original points of a semilinear graphs, we can create these maps which takes these points. So this takes this point into this point, is this coordinates into this number, and then deciding whether this linear function is negative or positive is basically just comparing two coordinates in some newly defined vector. And so this is very roughly one of the reasons, and then you have to argue that if you have some graph which depends on the sign pattern, then using just some basics from logic, you have some you can kind of union. So sorry, this was it's not very clear, but yeah, I don't really want to go into more detail about this. That's okay. So for those of you who are familiar with these techniques in the sky boundedness, you're usually happy when you see that your graph can be written as a union of graphs, and simply because if you know that if you have a graph which is a union of some graphs, and you know that each term in your union is sky bounded or almost sky bounded, then their union is also chi bounded or also chi bounded. So then you can just restrict your attention to these individual graphs. Yes. So now so let me write this. So this is some well-known facts that we know that we can write G as the union of G1 to Gk, then the chromatic number of G is at most the product of the chromatic numbers of G1 up to Gk. And also another nice thing is that if you know the clique number of G, that's also an upper bound of the clique number of G1 and Gk. So now if you you know the clique number of G1 up to Gk, so if you can prove a nice upper bound on the chromatic number, then it immediately implies some nice upper bound on the chromatic number of G as well. So in order to prove this, now you just need to prove that these kind of graphs are almost chi bounded. Okay. So now let me just rewrite the definition of a quasi-comparability graph. So G is a quasi-comp graph complexity is P. And the vertex set of G subset of RT times RT, and XY is joined by an edge to X prime, Y prime. If X is less than Y prime, or X prime less than Y. So now the main claim is that if G is like that, then the chromatic number of G is at most some constant times omega G, so the constant times the clique number of some constant times the log n to some other constant. And again, C and C prime only depend on this complexity T. Okay, so now let's prove this. So first, let's find a way how to actually imagine these quasi-comparability graphs. So I imagine is that let's just pick some coordinate I, and let's see. So let's see what just happens on this coordinate. So I imagine each vertex of G as kind of an interval. So here I have xi, yi. But of course, I could also have that yi is before xi, so there is nothing stopping that. And then also I have another point. It's also another interval. And so in this case, we have that yi prime is greater than xi. So if in all other coordinates this is true, then these are joined by an edge. Otherwise, they are not, because here yi is not bigger than xi prime. But as you can see, so this can be a bit annoying. There can be a few cases depending on how yi and xi are related to each other, whether one is yi greater than xi. But actually, after partitioning your vertex set into a constant number of parts, you can assume that if you look at the coordinates, then every point you either have xi is less than yi, or for every point you have xi prime less than yi prime. So either you have this case or you have this case for every point. So of course these intervals can intersect, so you cannot control them. So now let's say that we will define. So let's say that we define the type of a vertex with respect to how these endpoints of their intervals relate. So let's say that xi y has a plus type in coordinate I if xi is less than yi, and it has a minus if yi is less than xi. So in total, we have 2 to the t types. So after partitioning the vertex set into 2 to the t parts, we can assume that every vertex in every part has the same type. And now after we do this, we also want to partition the edge set of the graph. So again, we use this idea that if we can write our graph as the union of some smaller graphs which are nicer to handle, then we can prove something about their chromatic number, then again this implies what we want for the original graph as well. So let's consider some. Okay. So here let's just again focus on one coordinate, and let's look at what happens for types. So first of all, let's look at the negative type. So here you have yi, xi. So now if you have any chance that these two vertices are connected by an edge, then you need that xi is less than yi prime. So yi prime either needs to be here. So we either have this situation, or we have the situation where this is flipped. So if we know that these two intervals intersect, then we already know that they cannot be joined by an edge. So the only way they can join by this edge if one interval is completely to the left, to the other interval. So however, if we have plus, then we actually have two cases. So again, we can have that xi, yi is completely to the left, so xi prime and yi prime. Or we can have that these two intervals intersect. So this is somewhat visible. I know that this is just one coordinate, so this needs to happen simultaneously and simultaneously in the right order. So if I have that x is less than y prime, then I must have that in every coordinate, the interval corresponding to the first one is before the second, and also here as well. But in the case they intersect, then I have some freedom actually. But then this suggests that if we have some edge of this graph, then we can again assign a type to this edge. So given edge xy, y prime, we say that its type will be a subset Q of the index set where if I is in Q, then we have this situation that we have an intersection. Then these two intervals intersect each other. And if I is not in Q, then we have that so the interval corresponding to xy is before the interval corresponding to x prime y prime. And so again, this gives a partition of G into graph GQ, where Q runs over all possible subsets of T. And again, if you want to prove that this holds, then it's enough to prove that now we want that GQ is almost chi-bounded. And now we are almost finished, because now here you just need to look at this graph and you have to kind of visualize what this graph looks like. So as you can see, if you would only have these coordinates, the coordinates in Q, where the intervals intersect each other, then this would actually just be an intersection graph of boxes. This would be an intersection graph of boxes, which are the products of these intervals. However, if you look at these intervals, then you get a comparability graph. So you get the comparability graph where this is less than this in every coordinate. So in particular, you get a t-dimensional partial order. But then this means that GQ is the intersection of two such graphs. So you can write this as as B intersection C, where B is the intersection of boxes in RQ and C is a comparability graph. So here it's not even important that this is a finite dimensional comparability graph. This could be any comparability graph. And so what you would want to show that if you have such a graph, then this is almost chi-bounded. So now you need to be a bit careful, because if you take intersection for graphs, then this chi-boundedness doesn't translate the same way as if you would take for intersection or for unions. So you need to do something else. But actually, there is a simple divide and conquer argument which runs through the boxes. So somehow you can focus on the coordinates of boxes, and you can do a divide and conquer, which then will show you that GQ is, so you can show that GQ is almost chi-bounded. So again, this is a somewhat uninteresting routine argument. So I'm going to skip it, and then so this is very roughly the proof up to of course a bunch of technical details. And so already this proof and all this explanation took somewhat longer than I expected. So maybe then this is a good time to stop, and happy to hear questions if there are any.
Thank you very much.